In this video, we're going to look at some examples of how we can use recursion to solve problems. One example is using recursion to process a sequence, either a list or a string. And what's nice here is that sequences are inherently recursive. You can think of a string as a character followed by another string. You can think of a list as a single element followed by a list. And so what we can do is, if S is the sequence that we're processing, we can write the function so that it handles the first element of the sequence, S0, and so we'll do whatever needs to be done with it, and then we can make a recursive call to handle the rest. And this is often what we're doing with recursion. We're taking a smaller version of the problem and we're delegating its solution to the recursive call. We're letting the recursive call solve it. And in this case, we're going to get the rest of the problem by using a slice that begins at position 1 and goes all the way to the end of the sequence. We'll make a recursive call to process that slice. That will give us the solution to the smaller subproblem, and then we'll use that solution along with whatever we need to do with S0 to build the solution to the original sequence. Let's assume that we didn't have a built-in len function and we wanted to write our own mylen function that takes a string s and gives us its length. And we want to do this recursively. So to start by thinking about the base case, which is typically what you want to begin with, the question you can ask is, when can I figure out the length of a string s without needing to look at a smaller string? Again, we're asking ourselves, what is the simplest or smallest version of this problem? And in this case, it's when we have an empty string, a string of length 0. And notice there's nothing between the quotes here. So if the string s is equal to the empty string, we can just return 0 and we're done. That's the base case. If we don't have a base case, we're going to start by figuring out the length of the next smaller string. So as we said, we're going to take a slice starting at position 1 and going to the end of the string and pass that slice into the function mylen recursively. So that recursive call is going to figure out the length of the rest of the string. Now keep in mind, that call will lead to a whole sequence of recursive calls all the way down to the base case. And we'll see in a minute how that actually works out. But once those calls return, we will have the length of the shorter string. We're assigning it to a variable called len_rest. And then we need to ask ourselves, how can I use the solution to that smaller string, that length of that smaller string, to figure out the length of s? And because this smaller string is everything but the first character, the length of the full string is just len_rest plus 1. And so that's what we're going to return. Let's trace through the sequence of calls that will result from calling mylen on the string wow. So in this first stack frame, s is the string wow. We start the function, we don't have the base case, so we come down to the recursive case and we make a recursive call on the slice that begins at position 1. And so that gives us this call here, mylen on the string ow. That call gives us a new stack frame in which s is equal to the string ow, and we start the function over. We still don't have an empty string, so we come down and we execute the recursive case. And again, that involves taking a slice. But this time we're slicing this s, and so we're going to get an even smaller string, which is the string w. We call that function, we get a new stack frame in which s is equal to the string w. We start the function over. Still don't have the base case, so we come down and do another slice. And this time, when we're doing a slice of the string w beginning at position 1, because there is only one character in the string, you end up with the empty string. And so that's what gets passed into the next call, and we get a new stack frame for it in which s is the empty string. So at this point we have 4 different stack frames, each of which has its own variable s. And it also has a variable len_rest although we're not going to need that variable in this last call, because this last call, when we start the function over, we see that we do have the base case, and so therefore we just need to return 0. So that brings the recursion to a stop. Now watch what happens on the way back. Just like any other function call, the return value gets sent back. And where does it get sent back to? It gets sent back to that previous call in which s is the string w. So here was the call that we made. The return value is 0, and so that 0 gets assigned to len rest in this stack frame. And then we pick up where we left off, and we're going to return len rest plus 1, which is 1. And that is indeed the length of the string w. That return value gets sent back to this previous invocation. It replaces the function call. It gets assigned to len rest in this stack frame. And now, once again, we're going to pick up and return len rest plus 1, which is 2. And notice that is indeed the length of the string ow. That return value gets sent back to this call and replaces it and gets assigned to len rest in this stack frame. And then we pick up where we left off. We return len rest plus 1, or 3, and that is indeed the final result, the length of the string wow. Now let's look at how we can use recursion to raise a number b to a power p. I'm assuming that p is a non-negative integer, and b can be any number, either an int or a float. So again, for the base case, we want to figure out what the smallest version of the problem is. Another way to think about it is to ask a question like this one. When can I determine b to the p power without needing to know a smaller power? And we can do that when p is 0, because b to the 0 is always 1. Next, we need to figure out the recursive case, and we need to ask ourselves, how can we reduce the problem to a smaller version of the problem that would then be helpful in determining the solution to the original problem? And an easy way to do that here is just to subtract 1 from the exponent, p, from the power. Because if I know b to the p minus 1, I'll be able to figure out b to the p. So we make a recursive call in which we leave b alone, but we subtract 1 from the second input, the input p, and that's going to give us b to the p minus 1, and I'm taking that result and assigning it to a variable pow underscore rest. And then I need to do my one step, and in this case that just involves taking pow rest and multiplying it by another factor of b, because that will give me b to the p. And so that's what I'm going to return. Let's see it for a concrete case where b is 3 and p starts out at 3. So we don't have our base case, and so we come down and we make the recursive call and we subtract 1. So now the second input is 2. We get a new stack frame in which p is 2. Again, we come down to the recursive case, we subtract 1 again. That gives us a new stack frame in which p is 1. We still don't have our base case. We make another recursive call passing in 0, which gives us another stack frame. And here, finally, we hit our base case and we return 1. Now once again, the final result is going to get built up on the way back from the base case. And this is what happens in recursion. So the 1 gets sent back and gets assigned to pow rest, and then we pick up and we return b times pow rest. And so we end up returning 3 from that call. Notice that 3 is indeed 3 to the first. That gets sent back. We go back to the previous invocation. It gets assigned to this pow rest, the one in this stack frame, and we return 3 times 3, or 9, which is indeed 3 squared. That value gets sent back and gets assigned to pow rest in this stack frame, and we return 3 times 9, or 27, which is our final result.